Europa should be dead. It circles the sun more than 5 times farther out than Earth. Its surface temperature drops to nearly negative 160 degrees Celsius. It floats inside one of the most violent radiation environments in the solar system, Coot Jupiter's. From the outside, it looks like a broken white ball, pale, cracked, silent. Every instinct says, nothing lives there, nothing could, but beneath that broken ice, there may be an ocean, not a small lake trapped in rock, not a frozen pocket buried near the surface, a global ocean, hidden in permanent darkness, an ocean that may hold about twice as much water as all of Earth's oceans combined. And it has been there quietly for a very long time. 4520. NASA is flying there now. The spacecraft is called Europa Clipper. It launched in October 2024. It is on its way, but here is what it will not do. It will not land. It will not drill through the ice. It will never touch the ocean. It will arrive at the Jupiter system. And then it will fly past Europa again and again and again, each pass lasting only a few hours, each time skimming close, reading signals, measuring gravity, listening to the magnetic field, trying to understand an ocean it may never directly see. Imagine standing at the edge of a frozen lake, in complete darkness. You cannot break the ice, you cannot reach the water, but you can press your ear to the surface. You can feel the pressure from below. You can read what the ice remembers. That is what Europa Clipper is doing, pressing its instruments against the ice and listening. Jupiter fills the sky above Europa. It is enormous from Europa's surface. Jupiter would appear more than 20 times wider than the full moon appears from Earth, a planet so large it never fully sets. It simply hovers, pulling, always pulling. Europa itself is smaller than our moon, but scientifically, it may be one of the most important objects in the solar system. Its surface is bright, almost white, and it is covered in lines, long, dark fractures running in every direction. Some stretch for thousands of kilometers. They look like cracks in old porcelain, or veins, or wounds that never fully healed. Scientists call them lineae, but what they may really be is a record of the ice shifting, of tidal forces bending the shell, of something moving below, pressing up, pulling back, leaving its mark on the surface, in patterns we are only beginning to read. By every simple measure, Europa should not have liquid water. The sun is too far away. At that distance, sunlight arrives as barely a whisper, not enough to warm anything, not enough to melt ice. Standard logic says, the water froze, all of it, long ago, and yet, Europa is not alone out there. It orbits Jupiter, and Jupiter is not a gentle neighbor. Its gravitational field is immense, and as Europa moves around it, that gravity stretches and compresses the moon in a constant rhythmic cycle. This is called tidal flexing. The same process that makes Earth's oceans rise and fall operates here at a planetary scale, bending the moon itself, generating heat deep inside, not from sunlight, from gravity, from the slow, relentless squeezing of rock and ice over billions of years. And if there is enough heat below the ice, if the conditions are right, the water does not freeze all the way down. It stays liquid, in the dark, under pressure. A cold, salty, hidden sea, life as we understand it, needs three things: liquid water, a source of energy, the right chemistry. For most of human history, we assumed energy meant sunlight, but we were wrong. On Earth, some life survives far below the ocean surface. No sunlight, no sunrise, no day or night, only water, rock, heat, and chemistry. Europa raises a version of the same question, not whether life needs sunlight. We know now that some life does not, but whether the chemistry below that ice could substitute for everything the sun provides above, whether a world with no sunrise, no seasons, no warmth from its star, could still have the ingredients. That question does not have an answer yet, but it is exactly the question Europa Clipper is going to ask. Jupiter's radiation is one of the harshest environments in the solar system. High-energy particles stream outward from the planet, hit at extraordinary intensities at Europa's surface. That radiation would be lethal to an unprotected human very quickly. It tears apart molecules, it strips electrons from atoms, it rewrites the chemistry of anything it touches. For life on the surface, if anything tried to exist there, this would be a nightmare. But here is the strange part. That same radiation may be doing something useful when it strikes the ice and the surface molecules of Europa. It breaks them apart and reassembles them into new compounds, including oxidants, molecules that carry chemical energy, the same kinds of molecules that many forms of life on Earth use to drive the reactions that keep them alive. And if those molecules, created on the surface by radiation, can somehow migrate downward through the ice into the ocean below, then Jupiter's radiation, the very thing that makes the surface deadly, may be feeding chemistry in the dark, the danger above, becoming energy below. Europa Clipper will not answer everything in one pass. It was never designed to. The mission plan calls for nearly 50 close flybys of Europa over several years, each one different, each one reading a slightly different piece of the puzzle. It will look for shadows of the ocean, a pull in gravity, a bend in the magnetic field, a buried layer inside the ice, a trace of chemistry on the surface. Each flyby is a question, each instrument a different way of listening, not to the surface, through it. Europa is not asking the same question as Mars. Mars asks whether life once existed, whether long ago on a warmer and wetter planet, something began and then was lost. Europa asks something different. Europa asks whether a habitable ocean could still be there, right now, tonight, under the ice, in the dark, and if a liquid ocean can survive there, sustained not by sunlight, but by gravity and chemistry, hidden beneath kilometers of ice. Inside the radiation field of the largest planet in the solar system. Then maybe Earth was never the only kind of world where something like life could begin. Maybe the conditions we thought were rare are not rare at all. Maybe they are simply hidden. Let's stay with the ocean for a moment. Not the surface, not the ice, the ocean itself. We believe it exists because of what we can measure from far away, the way Europa responds to Jupiter's magnetic field, the way its surface has moved and fractured over time, the way its interior responds to Jupiter's gravity. None of this is a photograph of water. None of this is a sample. It is inference. It is the science of reading shadows, of seeing a shape in the dark, by the way it bends the light around it, and what those shadows suggest. Kut is an ocean that has been liquid for an enormous amount of time, not a brief thaw, not a seasonal melt, a body of water that may have persisted for hundreds of millions of years, perhaps longer. Inference is not the same as imagination. It is not a guess. It is a conclusion drawn from multiple independent lines of evidence, each one pointing in the same direction. When different kinds of measurements, the magnetic response, the surface geology, the gravity field, the behavior of the ice, all converge on the same answer, the answer becomes harder to doubt, and what they all suggest is a moon with liquid water inside, an ocean that has been there for as long as we can reasonably trace. The history of this moon, not a temporary thing, not a recent development, something old, something persistent, something that has outlasted more events on Earth than our species can meaningfully imagine, hidden, enduring, restless. The reason that ocean may still exist comes down to one force, gravity. Europa orbits Jupiter in a pattern that is not perfectly circular. It is slightly elliptical. This means that as Europa moves, the distance between it and Jupiter, Kant, changes, not by much, but enough. When Europa is closer to Jupiter, the gravitational pull is stronger. When it is farther away, the pull relaxes. This variation, this constant stretching and releasing, flexes the interior of the moon. Think of bending a metal spoon, back and forth, slowly, until it warms at the bend. That warmth is not coming from outside. It is coming from the friction of the material itself. Europa works the same way. Jupiter bends it, over and over, and that bending generates heat, not much by cosmic standards, but enough, possibly, to keep water liquid beneath several kilometers of ice. No star required, no sunlight, just gravity, doing what gravity does quietly. For billions of years, the elliptical orbit is not an accident. It is maintained by the gravitational interactions between Europa and Jupiter's other large moons, particularly Io and Ganymede. These moons orbit Jupiter in a pattern where their orbital periods are related by simple whole number ratios. Every time Ganymede completes one orbit, Europa completes exactly two. Every time Europa completes two orbits, Io completes four. This resonance keeps the orbits slightly elliptical. It keeps the tidal forces active. It keeps the heating going. It is a chain of gravity, linking three moons across millions of kilometers of space, and at the end of that chain, inside Europa, is the warmth that may keep an ocean liquid, the universe finding a way to provide energy where the sun cannot reach. The ice shell above that ocean is not thin. Current estimates suggest it may be kuntit, anywhere from a few kilometers deep to perhaps 30 kilometers or more. Scientists are not certain. That uncertainty is part of why Europa Clipper exists. But here is what that ice means in practical terms. It means the ocean is hidden behind a barrier we do not yet know how to cross. Maybe the surface and ocean exchange material. Maybe they do not. That uncertainty is part of the mystery. The ocean has no contact with sunlight, no exposure to open space. It exists in its own deep silence. beneath everything, untouched by anything we have ever sent there. And yet, hidden does not mean empty. Isolated does not mean dead. Some of the most surprising life-bearing environments on Earth, the count, are also cut off from the surface, deep inside Antarctic ice, far beneath the ocean floor, in rock, in darkness, in silence. Life finds its own terms. The ice on Europa is not a passive barrier, it is an active geological layer. It deforms, it flows on long timescales, it fractures under stress. It is possibly exchanging material with the ocean below through dune processes we do not yet fully understand. The lineae, those long dark fractures, may be places where that exchange is most visible, where ocean chemistry has reached the surface, where something from below has left its mark in the ice. The chaos terrain regions may be places where ocean influence has been most intense, where warmth from below has softened the overlying ice and allowed it to reorganize. Whether these features represent a direct two-way exchange or a one-way upward migration, or simply the distant influence of a warmer ocean on a cold surface, that is precisely what we do not yet know. And it is one of the most important things we might learn. So why not simply land on Europa? Why not send a rover drill through the ice and lower a camera into the water below? The answer is not one problem. It is several. The first is radiation. Jupiter's radiation environment is severe enough that any spacecraft operating on Europa's surface would absorb damaging levels of energy very quickly. Electronics degrade, instruments fail, a lander would need exceptional shielding just to survive long enough to operate. The second problem is the ice itself. Drilling through kilometers of ice on another world with no repair crew, no second attempt, using hardware that had to survive years of deep space travel before it even arrived, is not impossible in principle, but it is one of the most complex engineering challenges humans have ever considered. Maintaining a drill in a hostile environment, managing the water produced by melting, keeping a communications link open through kilometers of ice, preventing contamination of the ocean from microorganisms we might inadvertently carry there. Every one of these is a problem of the highest difficulty. And the third problem is time. We do not yet know enough about Europa to know where to drill. The ice varies in thickness, the surface chemistry varies, the tidal stress patterns vary. Sending a drill to the wrong location would tell us very little, and the cost of that mistake would be enormous, not just in resources, but in time. A mission to Europa takes years just to arrive. A drilling mission would take more years to develop. If it arrived and drilled in the wrong place, in a region of very thick ice, far from any active exchange with the ocean, the result might be a kilometers deep hole in an ice shell that told us nothing about the water below. First, we need to understand the whole moon, its patterns, its layers, its rhythms. We need to know where the ocean is closest, where the ice is thinnest, where the chemistry on the surface most strongly reflects what lies below. That is what Europa Clipper is for. It is the reconnaissance, the detailed mapping, the foundation on which the next generation of missions will be built. Europa Clipper does not orbit Europa. This is important. It orbits Jupiter. From that wide orbit, it periodically sweeps inward and skims close to Europa, sometimes passing within just a few hundred kilometers of the surface. Each flyby lasts only a matter of hours, but in that window, the spacecraft collects as much as it can. It reads the gravity field with enough precision to detect subtle changes in Europa interior. It measures the magnetic environment, looking for the disturbance that a large body of salt water would leave in the field. It scans the surface chemistry, searching for compounds that may have been touched by what lies below, and it uses radar, sending signals downward through the ice, waiting for them to bounce back, reading the echoes to map what is buried inside. Each flyby is a layer. Each pass adds something, not answers. At first, only data, and from data, slowly, a picture forms. The flybys are not all identical. Each one is designed with a specific purpose, a specific region to fly over, a specific altitude, a specific set of instruments configured for what that particular pass can best achieve. One pass might prioritize the radar, flying at the altitude that gives the best ice-penetrating geometry over a region of chaos terrain. Another might focus on the gravity field, passing in a way that allows the most precise gravitational measurements of the ocean's response below. Another might center on chemistry, skimming close enough that the spectrometers can read the faintest molecular signals from the surface compounds below. Each flyby is carefully designed, months of planning for a few hours of observation, and each one leaves behind a swath of data that scientists on Earth will spend months analyzing. There is something quietly extraordinary about the way this mission works. A spacecraft traveling hundreds of millions of miles from Earth, flying past a moon, again and again, trying to read an ocean through kilometers of ice, kern, from hundreds of kilometers above, in a few hours of close approach, before swinging back out into the wider darkness of the Jovian system. It will take years. The answer, if it comes, will not arrive in a single transmission. It will be assembled slowly, piece by piece, flyby by flyby, inference by inference. This is how science works. At the edge of what is reachable, not with certainty, with patience, with instruments pointed at a surface that gives almost nothing away, and taking careful note of the very little it does. And still we ask, still we listen, still we send something across the dark, just to find out. What is there? The mission will last several years, dozens of flybys, an enormous volume of data. Each piece of data will be transmitted back to Earth across hundreds of millions of miles, a journey that takes light between 35 and 52 minutes, depending on the positions of the planets. The signal is faint by the time it arrives. The dishes of the Deep Space Network, large radio antennas situated at 3 sites around the world, will receive that signal, and the engineers and scientists will decode it, verify it, distribute it to the teams who are waiting to analyze each specific measurement. And then the work of interpretation begins, comparing what was measured against what the models predicted, looking for agreement, looking for discrepancy, looking for the unexpected reading that changes the picture. Science at its most patient At its most deliberate, at its most careful, we have been trying to understand Europa. For decades, the Voyager spacecraft caught glimpses of it. In 1979, the Galileo spacecraft studied it more closely. In the 1990s and early 2000s, each mission added to what we suspected, but suspicion is not the same as knowing. Europa Clipper is the most capable mission we have ever sent toward this moon, and still, even with everything it carries, it will not touch the ocean. It will pass over the ice, read the shadows, listen to the field, and send everything back to us across hundreds of millions of miles through the long silence between Jupiter and Earth, so we can piece together a picture of something no instrument, no camera, no human hand has ever reached. The ocean is there, we believe it is there, and somewhere in the data, that Europa Clipper is already beginning to gather. The answer may already be forming, quietly, in the numbers, in the signals, in the slow, careful reading of an ice shell that has kept its secret for longer than our species has existed. Look at the surface of Europa. Really look at it. Not the way you might glance at a photograph taken from a spacecraft traveling quickly past. The way you look at something when you are trying to understand it. When you know that what you are seeing is not the whole story. When you suspect that the surface is only the beginning of something much larger and much older and much stranger than anything visible from above. The first thing you notice is the brightness. Europa is one of the most reflective objects in the solar system. Its surface returns nearly 2/3 of the sunlight that strikes it. That is an extraordinary amount. Most rocky and icy bodies in the solar system are dark by comparison. Our own moon absorbs most of the light that hits it. It looks gray and ancient and worn, pocked with craters, coated in dark dust. Accumulated over billions of years, Europa looks almost white, like a sphere of compressed snow, like a polished surface, seen from a very great distance, bright enough to stand out even against the glow of Jupiter nearby. That brightness is one of the first clues that something is different here. A surface genuinely old, one that has been sitting exposed in space for billions of years, should not look like this. Space exposure darkens surfaces. Radiation chemically alters the uppermost layers. Micrometeorite impacts grind the surface into fine, dark dust over time. Europa's surface is fresh, or at least freshened, continuously renewed by processes we are still working to understand. For a moment, that brightness makes it look simple, clean, featureless, the kind of surface you might expect on a world that has been frozen solid for billions of years, undisturbed, unremarkable, a ball of ice slowly orbiting in the cold. But it is not featureless. Let the distance close. Let the details emerge slowly, as if you are descending toward the surface on a long, slow approach. Through empty space, the broad white disk begins to resolve into something more complex, something more layered, something that takes longer to read. The closer you get, lines appear, dozens of them at first, then hundreds, crisscrossing the surface in every direction, layering over one another, some faint and thin as hairlines, others wide and darkly colored, reddish-brown against the white, like old rust spreading across clean metal, like veins visible just below pale skin, like the finest cracks in an old painting where the surface has shifted over centuries and the paint has followed. They go on for thousands of kilometers. Some of the longest stretch farther than the width of entire continents on Earth. They are not random. They curve, they arc, they intersect at angles that suggest not chaos, but process, pattern, a surface that has been stressed and cracked and filled and stressed again over and over across an enormous span of time. The surface is not blank. It is written on in a script we are only beginning to learn to read, in a language whose alphabet is fracture and pressure, and the slow movement of ice over a world that has never been truly still. There is something worth noting about what brightness means here. When we talk about reflectivity, when we say Europa reflects 2/3 of the sunlight that strikes it, we are talking about a property called albedo. And Europa's albedo is remarkably high. Most objects in the solar system that have existed for billions of years are dark, comets are dark, asteroids are dark, the surface of our moon is dark. Darkness accumulates, space weathering, the slow chemical alteration of surfaces by solar radiation and micrometeorite bombardment tends to darken things over time. Europa resists that darkening. Its surface is being continuously refreshed. New ice emerges at the surface. Old material is cycled away. The brightness is not just an aesthetic quality. It is evidence of process, evidence of renewal, evidence of a world that cannot simply sit still and let time accumulate on its surface. The way it does on a quiet, dead rock, something below keeps pushing up, the surface responds, and the result, seen from far away, is this remarkable whiteness, this unusual, almost artificial seeming brightness that hints at a world that is more active than it appears. One of the most striking things about Europa's surface is how young it looks. Not young in human terms, young in planetary terms. When geologists study a surface in the solar system, on the moon, on Mars, on an asteroid, one of the first things they count is the number of impact craters. Every time an asteroid or comet strikes a surface, it leaves a scar. Over billions of years, those scars accumulate. The older the surface, the more craters it carries. The less active the surface, the longer those craters persist. The moon is ancient in this sense. Its surface is covered in craters, a record of every major impact since the solar system was forming. Its highlands, the pale elevated regions, are among the oldest terrain in the solar system. They have barely changed. In 3.5 billion years, Mars has craters too, different ages in different regions, telling the story of how different parts of the planet have been geologically active at different points in its history. Europa has almost none. For a moon orbiting Jupiter, a planet whose immense gravity attracts debris from across the solar system. A planet that has been pulling in comets and asteroids for 4.5 billion years. The near absence of craters on Europa is remarkable. The surface should be covered, pocked and scarred like the ancient highlands of the moon, worn by billions of years of incoming rock and ice. Instead, it is almost clean, which means something has been erasing the old impacts, generating new material, replacing the ancient record of bombardment with something fresh. The best estimates from planetary scientists suggest that Europa's surface is geologically recent, probably less than 100 million years old, possibly much younger in some regions. In planetary terms, that is astonishing. It means the surface we see today was not there when dinosaurs walked the Earth. It is younger than many of the mountains we hike on our planet. It is a fresh expression of whatever process is continuously renewing this moon's exterior. That process is driven from below, and the dark reddish-brown lines, the lineae, are among its most visible signatures. They are not random cracks. They are structured features. They have width. They have color. They have chemistry. Their color comes from material that is not pure water ice, salts, possibly, sulfur compounds, minerals that either rose from deeper in the moon or were created by the relentless radiation that bombards the surface from Jupiter. Where that material comes from exactly is one of the questions Europa Clipper is designed to answer, but the lines themselves, the pattern of them, the way they layer and cross and curve, tell us something important even before we know their exact chemistry. They tell us this surface has been opened repeatedly along many different axes at many different times, leaving behind a record of every stress the ice has ever experienced. Trace one of the longer linea with your eye. Follow it across the surface as if you were flying slowly above it. Low and unhurried, watch it curve gently over hundreds of kilometers. Watch it cross an older line, cutting through it clearly, younger than what it intersects. Watch it fade, and then reappear, as if whatever opened it came and went and came again. You are following a record of tension, of the ice reaching its limit and splitting open, and something moving through, something that left color, left chemistry, left the visible record of a world that has never stopped working on its own surface. The absence of craters is telling us something specific. When a large impact occurs on a planetary body, it does not just leave a hole. It generates a complex structure, a central depression, raised rim walls, sometimes a central peak, sometimes a pattern of ejecta, spreading outward in long rays. These structures persist for billions of years on inactive surfaces. On the moon, you can trace the ejecta rays from craters that formed over 3 billion years ago. On Europa, the few craters that do exist look different from what you'd expect. They tend to be shallow relative to their diameter. The surface has partially relaxed beneath them, as if the ice was warm enough to slowly flow back after the impact and soften the topography. Even the craters that do exist have been modified by the same process that erases the older ones. This tells us the ice is not cold and static all the way down. It is warm enough somewhere to allow slow flow, warm enough to let the surface recover, warm enough to smooth out the evidence of ancient collisions. The ice remembers warmth from below, and it shows that memory in the strange flatness of its craters, caught in the redness of its lines, in the chaos of its disrupted terrain. There are regions on Europa where the surface has not just cracked, but broken apart entirely. Scientists call these areas chaos terrain. The name is accurate. In the chaos regions, The smooth, bright ice of the background surface is gone. What remains looks like a scene of disruption, preserved in place, large irregular blocks of ice, tilted at slight angles from one another, some raised higher than their neighbors, others lower, each one separated from the next by a matrix of finer material, possibly refrozen slush that fills the gaps between them. The whole arrangement looks like something that was once in motion and then stopped suddenly, like pack ice on a polar sea that was drifting and shifting in the dark, and then flash froze, locking everything in mid-drift, like a mosaic that was shaken, then set in whatever new configuration the shaking produced. What caused the chaos terrain? The most widely discussed explanation involves what lies below the surface. If there are regions where the ice shell is thinner, where the ocean beneath is closer to the surface, then heat from below could soften the overlying ice. The rigid outer layer could crack, blocks could tilt and shift on a substrate of warmer, more yielding ice. And then, as conditions changed, as the heat source diminished, for as the region moved away from the most active zone, everything could refreeze, locking the blocks in their new positions, preserving the record of that movement in a landscape of fractured, tilted geometry. If this explanation is correct, and it has strong support among planetary scientists, then the chaos terrain regions are not just interesting surface features. They are surface maps of the ocean's influence, not windows into it. The ice is still there, still thick, still frozen, but records, geographical records, of where the ocean's warmth and dynamics have been most strongly felt. At the surface, there are also double ridges, long pairs of raised lines, running in parallel across the surface, deep with a shallow valley between them, extending for hundreds of kilometers, in gentle, sweeping curves. One leading explanation is that warm ice, or possibly liquid water, was pushed upward through a crack from below as it reached the colder surface environment. It froze on the margins of the crack, building up the two raised ridges on either side, a mountain range built from the inside out, not by colliding plates of rock, not by volcanic eruption in the usual sense, but by material from below, forcing its way up through a fracture and freezing at the margins of that forced opening. The ridges stand quietly now, frozen, still, but they record a moment when the interior of this moon was pushing upward, trying to reach the surface, leaving behind its raised traces in the ice above. Taken together, the lineae, the chaos terrain, the double ridges, the near absence of ancient craters. Europa's surface tells a consistent story. This is not a dead world. This is not a place that froze billions of years ago and has been inert ever since. This is a world whose surface is being continuously shaped by processes that originate far below it, a world that carries its interior written on its face, flying slowly above Europa, following one feature to the next, a ridge to a fracture to a chaos region, to another ridge. You are reading a history of pressure and motion, and the slow, continuous work of a moon that has never fully stopped. The chaos terrain regions are not evenly distributed across Europa's surface. They tend to appear in certain areas more than others, Some scientists have proposed that the distribution of chaos terrain may reflect areas where the ice shell is thinnest, where the ocean below is nearest, where the ocean is close to the surface. The ice above it is warmer. Warmer ice is weaker ice. Weaker ice is more likely to fracture and move. So the pattern of chaos terrain may itself be a map, a rough map of the ocean's geography, drawn in the disrupted surface above it, where chaos is concentrated. The ocean may be closest, where the surface is smooth and unbroken. The ocean may be deeper, the ice thicker, the connection between the two more attenuated. Europa Clipper will measure the thickness of the ice in chaos terrain regions and compare it to adjacent smooth terrain. If the ice is indeed thinner where chaos occurs, that would confirm the hypothesis. It would also identify those regions as the most likely sites for any future mission that wants to get as close to the ocean as possible. For now, from the surface, we can only read the chaos as what it is, a record of disturbance, frozen in place, waiting to be interpreted. Now leave the surface, go downward, through the bright ice, through the fractures and the ridges, and the refrozen chaos, down into the material of the moon itself. The ice shell of Europa is not a single uniform layer. It has internal structure. It has depth. It behaves differently at different depths, and understanding that structure, its thickness, its temperature gradient, its internal dynamics, is one of the central goals of the Europa Clipper mission. Near the surface, the ice is cold, extremely cold. At Europa's surface temperature, around -160 degrees Celsius, ice is brittle. It does not bend. It does not flow. It fractures cleanly under stress, the way glass fractures, leaving sharp edges and clean breaks. This is the layer we see from above, the layer that forms the lineae and the chaos blocks and the sharp margins of the double ridges, the layer that cracks open when tidal forces stretch the moon beyond what the ice can withstand in that instant. But as you go deeper, as the temperature rises slowly, degree by degree, due to heat rising from below, the ice begins to change. At some depth below the surface, the ice becomes ductile. Ductile ice does not fracture cleanly under pressure. It deforms, it flows slowly, the way glaciers on Earth flow, toward lower ground over thousands of years. Not fast, not visibly, but persistently, over geological time, ductile ice moves. This deeper, warmer, more yielding ice can convect, carrying heat from below upward, the way heated material rises through a viscous fluid. Warm blobs of ice rise, cooler material sinks, a slow circulation that moves heat from the bottom of the ice shell toward the top, the boundary between the brittle upper ice and the ductile lower ice is not sharp. It is a gradual transition, a zone where the character of the ice changes from rigid to yielding. Scientists debate where this boundary sits. How thick is the brittle layer? How thick is the ductile layer below it? The answers depend on how much heat is rising from below, and that depends on the strength of the tidal heating, which in turn depends on the internal structure of the moon's rock count, the composition of the ice, and several other factors that we do not yet know precisely. This is why radar measurements are so important. Different temperatures and compositions of ice reflect radio waves differently. The radar on Europa Clipper will probe downward through the shell, reading the structure layer by layer, building a picture of how thick each zone is and where the boundaries lie. And below the ductile ice, below all of it, is what scientists believe is water, liquid, not warm by any comfortable standard, cold, in fact, but not frozen, pressurized by the enormous mass of ice above it, in contact with rock below, a global ocean. The word global means something specific here, not a lake, not a sea in a basin, not a regional body of water, an ocean that wraps entirely around the interior of the moon, covering every part of the rocky seafloor below, extending under every part of the surface above, unbroken, connected, a single continuous body of water surrounding the rocky interior of a moon the size of Earth's moon, no shoreline, no coast, no place where the water meets the air, only ice above, rock below, and between them, in pressure and in permanent darkness, water. The ductile ice below the brittle surface is not a uniform layer either. In a convecting ice shell, one where the ice is warm enough to flow and circulate, there may be structures called diapers. A diaper is a blob of buoyant material that rises through denser material above it. In Europa's ice shell, a diaper would be a region of slightly warmer, slightly less dense ice that rises upward through the colder, denser ice above. As a diaper rises, it brings heat from below, closer to the surface. It can soften the brittle layer above it. It can cause the surface ice to fracture and displace. It may be diapirs, rising blobs of warm ice that create the chaos terrain. As a diapier rises beneath a region of the ice shell, the surface above it softens. The blocks of brittle surface ice tilt and shift over the softening zone. When the diaper cools or the dynamics change, everything refreezes. In the new displaced configuration, a chaos region, seen from above, a diapier, seen from inside, the same event, the same process, two perspectives on the same geological story. This is the kind of understanding that comes from combining surface observations from above with subsurface measurements from radar, the two together building a picture that neither could provide alone. The depth of this ocean is not known with certainty. Current scientific models suggest it could be somewhere in the range of 80 to 170 kilometers deep. If those estimates are correct, then Europa's ocean contains roughly twice as much liquid water as all of Earth's oceans combined. Hold that number for a moment. Earth's oceans are vast. They cover more than 70% of our planet's surface. Their average depth is nearly 4 kilometers. Their deepest point, the Challenger Deep in the Mariana Trench, descends nearly 11 kilometers below the ocean surface. Europa's ocean, if the models are right, may contain twice that total volume. Not because Europa is larger, it is smaller than Earth, but because the ocean wraps entirely around the interior, and because it is deep, extraordinarily deep. Possibly 100 kilometers or more of liquid water under a shell of ice, an ocean of that scale, has had an enormous amount of time to develop its own dynamics, its own circulation patterns, its own chemistry. And it has had that time not for millions of years, but possibly for hundreds of millions. While on Earth, Life was evolving its first complex cells, the first organisms with nuclei, with membranes, with internal structures. Europa's ocean may already have been in roughly this state, while fish were appearing in our ancient seas. Europa's ocean was cycling, while forests were spreading across the continents of a young Earth, feet, while great reptiles ruled, while mammals spread after the mass extinction that ended the age of dinosaurs, while our own ancestors appeared and spread across the African continent. Europa's ocean was there, cycling, moving, in the dark beneath its ice, unchanged in its fundamental nature, a body of water so ancient that our entire recorded history is a fraction of its age. The vastness of Europa's possible ocean becomes more significant when you consider its age. An ocean that has been liquid for hundreds of millions of years or longer is an ocean that has had time to develop complexity, chemical complexity, physical complexity, the kind of layering and differentiation that emerges in any system. Given enough time on Earth, our ocean has developed thermoclines, temperature boundaries between shallow warm water and cold deep water. It has developed chemical gradients. It has developed currents that circle the globe, distributing heat and chemistry. From one region to another, all of this took time. Billions of years of the ocean responding to sunlight and wind, to continental boundaries, to the chemistry of the seafloor. Europa's ocean has had similar time, not the same forcing, not sunlight and wind, but tidal heating and seafloor chemistry, and the slow circulation of water across the interior of a moon. What has it built in that time? What chemical complexity has accumulated in an ocean that has been cycling since before our species existed? We do not know, we cannot know yet, but the question is not absurd. It is pointed, it is aimed at something real, and Europa Clipper is the first step toward an answer. The ocean, as we understand it, is almost certainly not pure water. Water that has been in contact with rock for hundreds of millions of years is not the same as water freshly melted from ice. It dissolves things. Rock releases minerals slowly, too slowly to notice in a human lifetime, but relentlessly over geological time. Salts, metals, sulfur compound, magnesium, calcium, iron, and other elements freed by the gradual chemical interaction between liquid water and the minerals of the seafloor. On Earth, our oceans are salty for exactly this reason. Billions of years of water flowing over and through rock has carried dissolved material to the sea. The sea has concentrated it, built up its mineral inventory, layer by layer, year by year, ion by ion. Over geological time, Europa's ocean may have done the same. It has had the time, it has had the rock, it has had the water. And if the ocean is salty, if it carries dissolved minerals in the way that liquid water naturally does, when in sustained contact with rock, then it would be electrically conductive. Salt water conducts electricity. This is not an exotic property. It is why salt water can short out electronics. It is why the electrolytes in our bodies allow nerve signals to travel. Dissolved ions, electrically charged particles, move through salt water. In response to electrical forces, the ions carry charge. The salt water becomes, in effect, a liquid wire, and a large body of moving, Conductive salt water responds to external magnetic fields in a way that is measurable from the outside when an alternating or changing magnetic field passes through a conductive material, quantite. It induces electrical currents in that material. Those currents produce their own magnetic field, a response field that pushes back against the external field in ways that depend on the size, conductivity, and location of the conductor. Jupiter's magnetic field passes through Europa continuously. It is always there, always varying as Jupiter rotates and the field geometry changes relative to Europa's position, and scientists studying data from the Galileo spacecraft in the 1990s and early 2000s found exactly that response in Europa's magnetic environment, a signal that could not be explained by the moon's rocky interior alone, a signal that required something conductive, something large, something that wrapped around the entire interior of the moon and responded to Jupiter's changing field as one coherent body. The most natural explanation was a global saltwater ocean. We do not see it. We see the shadow it casts. In Jupiter's magnetic field, an invisible ocean made briefly detectable by electricity and salt, and the response of conductive water to the field of a giant planet more than 500 million miles away. That magnetic shadow is one of the most compelling lines of evidence for the ocean's existence, and it points to an ocean that is not local, not partial, but global, encircling the entire moon, responding as one body. The magnetic response that hints at the ocean was discovered by accident. In a sense, the Galileo spacecraft was not specifically designed to find Europa's ocean. It was designed to study the Jupiter system as a whole, the planet, the moons, the magnetosphere. But when scientists analyzed the magnetic field data collected during Galileo's flybies of Europa, they noticed something unexpected. The magnetic field around Europa was not behaving the way it should. If Europa were simply a rocky, icy moon with no special internal properties, it was varying, changing direction and magnitude in a pattern that correlated with Jupiter's rotating magnetic field. The induced signal, the response of some internal conductive layer to the driving external field, was there, measurable, consistent, and when they calculated what kind of internal structure could produce that response, the answer pointed to a global saltwater ocean, not a prediction confirmed, a discovery made. The scientists working with the Galileo data were not setting out to prove the ocean existed. They were simply analyzing the data, and the data told them something they had to take seriously. This is how science often works at the frontier, not with the expected confirmation of what was already believed, but with the unexpected signal that changes what you believe. Europa Clipper's magnetometer instruments are far more sensitive than Galileo's. They will make these measurements with much greater precision. They will be able to characterize not just whether the induced signal is present, but what it tells us about the depth, conductivity, and extent of the ocean that produces it. Water is necessary, but water alone is not sufficient. This is one of the most important principles in the study of potentially habitable environments. Imagine a glass of clean water. sealed in a container, placed in a room with no light source, left undisturbed. Nothing happens to it, nothing organizes inside it, nothing grows. The water remains water, the chemistry settles. The molecules reach a state of equilibrium and remain there indefinitely. Water provides the medium, the environment where chemistry can happen, where molecules can move and meet and interact, where reactions can occur that would be impossible in a solid or too diffuse in a gas. But chemistry does not drive itself. It needs energy, not energy in a vague, general sense, specific energy, the kind that creates differences, gradients, between one condition and another, hot and cold, oxidized and reduced, mineral rich and mineral poor, one side of a membrane versus the other. Life, at its most fundamental level, builds itself across those gradients. It is an elaborate chemical machine for exploiting the differences between one environment and another, taking in materials from one side of a chemical difference, releasing products on the other side, capturing the energy released in the process, using that energy to maintain and reproduce itself. On Earth's surface, the source of those gradients is ultimately the sun. Sunlight drives photosynthesis. Photosynthesis creates organic compounds, molecules with stored chemical energy. Those molecules are eaten. The energy moves through food chains. The entire living surface of our planet, from forests to coral reefs to soil bacteria, runs ultimately on solar energy, converted and reconverted through millions of different biological forms. Europa's ocean has no sunlight. The ice above blocks every photon. The ocean exists in a darkness so complete that no visible light has ever entered it. In the entire history of the moon, for anything in the ocean to be chemically active, for the water to be anything other than cold, mineralized, equilibrated water, there must be another energy source, something driving gradients, something keeping the chemistry from settling, something to exploit. And there is a candidate, the same force that keeps the ocean from freezing, gravity, tidal heating, the energy of Jupiter's gravitational field, converted by friction inside the moon into persistent warmth, warmth that rises from the rocky interior, warmth that reaches the seafloor, warmth that creates a temperature difference between the bottom of the ocean and the ice above, a gradient, a driver, a source of energy that has nothing to do with sunlight. The concept of energy gradients is worth sitting with for a moment. Life does not just need energy in the abstract. It needs energy in a specific form, a form it can intercept and use. A match burning in a room contains energy, but that energy, released quickly as heat and light, cannot directly power a bacterium. What life needs is a gradient, a situation where some chemical is in a higher energy state on one side of a barrier and a lower energy state on the other. The transition from high to low releases energy in a controlled way that biological molecules can capture. On Earth's surface, photosynthesis captures the energy of photons and stores it in chemical bonds. That is a gradient, light on one side, organic chemistry on the other, in deep ocean hydrothermal environments. The gradient is chemical. reduced compounds in the hot vent fluid, encountering oxidized compounds in the cold ocean water. That chemical mismatch is exploitable. Life has evolved enzymes that can capture the energy of that transition. For Europa, the question is whether any such gradient exists. Tidal heating provides heat from below. That heat creates temperature differences. Those temperature differences drive chemical differences. As water at different temperatures dissolves different amounts of minerals, has different chemical potential. A temperature gradient is a chemical gradient, and a chemical gradient is potentially exploitable. Whether it is exploited by anything is a question for another era of exploration, but whether it exists at all is something Europa Clipper may be able to constrain. Think about what tidal flexing means. In physical terms, Europa's orbit around Jupiter is not perfectly circular. It is slightly elliptical, stretched into an oval by the gravitational influence of Jupiter's other large moons, particularly Io and Ganymede, which orbit in a resonance that continuously perturbs Europa's orbit, preventing it from circularizing into a shape where tidal forces would cease. As Europa moves around Jupiter, the distance between them changes. When Europa is at its closest point, its periapsis, the gravitational pull from Jupiter is slightly stronger. The moon is squeezed a little tighter. Its shape distorts toward Jupiter more than at other points in its orbit. When it is at its farthest point, its apopsis, the pull relaxes. The moon returns closer to a sphere. This variation happens every orbit, every 3.5 days. Every 3.5 days. Europa is pulled and then released, stretched and then relaxed, deformed and then allowed to recover, over and over, without stopping. For as long as Europa has been in this orbital configuration, which is to say, for much of the history of the solar system, that repeated deformation generates heat through internal friction. The rock and ice resist the deformation. They are not perfectly elastic. They flex, but not without cost. Some of the energy of the deformation converts to heat rather than being stored as elastic energy. It is the same principle as bending a thick metal rod back and forth. The metal warms at the point of bending. You are putting mechanical energy into the rod, and some of that energy converts to heat through internal friction. Europa's interior heats the same way, not dramatically, not at the volcanic scale that Io, the innermost large moon, experiences. Io is so strongly tidally heated that it is the most volcanically active body in the solar system. Europa is farther from Jupiter. Its tidal heating is more modest, but it is there, and it may be just enough warmth rising from below to keep the base of the ice shell liquid, to maintain an ocean that would otherwise freeze, and that warmth, the caltid rising from the rocky interior through the ocean above it, creates the temperature gradients that drive circulation. Warm water rising from the seafloor, cooler water sinking from the ice above, a slow global circulation driven by nothing more than temperature difference and the relentless force of gravity. In moving water, Katit chemistry happens. In circulating water, minerals and compounds are transported. In a water column with a temperature gradient, the conditions for complex reactions exist. There is a detail worth noting about the orbital resonance that keeps Europa's orbit elliptical. The resonance between Io, Europa, and Ganymede is called the Laplace resonance, named for the French mathematician Pierre-Simon Laplace, who described the gravitational dynamics of the Jupiter-Moon system in the early 19th century. For every orbit that Ganymede completes, Europa completes exactly two. For every orbit that Europa completes, Io completes two. This 1-to-4 ratio is not a coincidence. The moons have fallen into this pattern through their gravitational interactions over billions of years, and once they reached it, they stayed. The resonance is self-reinforcing. If one moon drifts slightly, the gravitational tugs from the others push it back. The pattern is stable. It has probably persisted for most of the history of the solar system. And the consequence for Europa is that its orbit remains elliptical. Its tidal flexing continues. Its internal heat source persists without the resonance. So, Europa's orbit might have circularized. Tidal flexing would have diminished. Internal heating would have faded. And the ocean, if there ever was one, might have frozen. Three moons, locked in a gravitational relationship for billions of years, may be the reason. One of them has a liquid ocean today, gravity as the ultimate preserver, the resonance as the keeper of water. At the bottom of Earth's oceans, there are places where the seafloor cracks, where the tectonic plates spread apart and expose the hot mantle rock below, where seawater seeps down into those cracks, where the heat and pressure and chemistry of the rock transform the water, altering its composition, loading it with dissolved minerals, changing its temperature dramatically, and where that transformed water rises back up, emerging from the seafloor in a jet of hot, mineral-rich fluid. It meets the cold ocean above and creates a structure, a hydrothermal vent. At some of these vents, the mineral-rich fluid cools so quickly upon meeting the cold ocean that the dissolved minerals precipitate out immediately, building tall chimneys of mineral deposits, towers of sulfide and oxide minerals, rising from the seafloor like industrial chimneys in the deep dark. The fluid emerging from these chimneys can be extremely hot, hundreds of degrees Celsius in some cases, a feat made possible only by the enormous pressure at depth, which prevents the water from boiling, even at such temperatures, around these chimneys. In the complete absence of sunlight, miles below the surface, with no photosynthetic life nearby, there are organisms, entire communities, bacteria that extract energy from the chemical reactions between the vent fluids and the surrounding water, not from light, from chemistry, from the difference in oxidation state between the rising hot fluid and the cold oxygen-rich water above, and feeding on those bacteria, tube worms, shrimp, crabs, fish, an ecosystem sustained not by a star, but by a crack in a rock, in the darkness at the bottom of the sea. We are not saying Europa has this. We do not know. We have not been there. We have not measured the seafloor. We cannot yet say whether hydrothermal activity occurs there. But the conditions that make hydrothermal activity possible on Earth, heat from below, liquid water above, rock in sustained contact with water, may be present on Europa. Tidal heating warms the rock. An ocean sits above the seafloor. The water has been in contact with that rock for hundreds of millions of years at minimum. If any hydrothermal activity exists at Europa's seafloor, even modest, diffuse warmth, rather than dramatic black smoker venting, it would create exactly the kind of chemical environment that could, in principle, support the kind of chemistry we see sustained in Earth's deep oceans. Not certainly, not confirmed, but plausibly. And then there is the surface. Jupiter's radiation continuously strikes the ice. High-energy particles from Jupiter's radiation environment break apart molecules. They force chemistry. That would not happen without that energy input. Among the products, oxidants, reactive molecules that carry chemical energy, hydrogen peroxide, oxygen compounds, species generated when radiation attacks the water ice of Europa's surface and breaks it into its components on Earth. Oxidants are central to the metabolism of complex life. They are part of cellular respiration, the process by which living cells extract energy from organic molecules. If Europa's surface generates oxidants continuously, and if those oxidants can somehow move downward through the ice into the ocean, carried by slow ice cycling, or by fracture filling, or by some other exchange process, then the ocean would receive a steady chemical input from above, a supply of reactive chemistry generated at the surface by the same radiation that makes that surface so unwelcoming, the danger above, becoming in a slow and indirect way a potential resource below. There is a quiet irony in the chemistry of habitability. Jupiter's radiation is one of the things that makes Europa's surface so hostile. It tears apart molecules, it strips electrons, it makes the surface dangerous, and yet that same radiation may be manufacturing the chemical oxidants that the ocean needs as an energy source. The danger is also the supply chain on Earth. We produce oxygen through photosynthesis. Green organisms take carbon dioxide and water, use sunlight to pull the molecules apart, and release oxygen as a byproduct. That oxygen then fills the atmosphere. Other organisms breathe it. They use it as an oxidant, a molecule to react against. When breaking down food for energy, Europa has no photosynthesis. It has no green life, but it may have something functionally analogous. Radiation chemistry at the surface, breaking apart water molecules and producing reactive oxygen compounds instead of photosynthesis producing oxidants. Radiation chemistry produces oxidants, different mechanism, potentially similar result. The ocean, if it receives these oxidants, has a chemical energy source, not from life, but potentially for life, or for chemistry that precedes life. And the source of all of it is the radiation that makes the surface so unwelcoming, the hostile, and the hospitable, intertwined at every scale. From the largest, the gas giant whose gravity warms the moon, to the smallest, the particles whose radiation creates the chemistry, Europa is a system, every part connected to every other, the danger and the possibility, inseparable to understand Europa. You have to understand Jupiter, not as a distant light source, not as a beautiful backdrop in a photograph, as a physical environment, an active, dominating presence that shapes everything within its influence. Jupiter is the largest planet in the solar system, more than 11 times wider than Earth. More than 1,300 Earths could fit inside its volume. Its mass is greater than the combined mass of all other planets in the solar system, with more than room to spare. It is not a rocky world. It has no solid surface to stand on. It is made almost entirely of hydrogen and helium, the same elements that make up the Sun. If it had been about 80 times more massive, it might have ignited nuclear fusion and become a second star. Instead, it is the largest of a class called gas giants, worlds of gas and liquid, with no hard boundary between atmosphere and interior. As you descend into Jupiter, the gas becomes denser and hotter. At some depth, hydrogen, normally a gas, is squeezed into a liquid at still greater depths. It is compressed into a state where it conducts electricity like a liquid metal. It is that metallic hydrogen deep in Jupiter's interior that generates the planet's magnetic field. As Jupiter rotates, completing one full rotation in just under 10 hours, faster than any other planet in the solar system. That vast rotating core of conductive liquid acts like a generator. It produces a magnetic field of extraordinary strength. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, and it does not confine itself to the space near Jupiter. It extends outward, far outward, the region of space dominated by Jupiter's magnetic influence. The magnetosphere is one of the largest coherent structures in the solar system. If you could somehow visualize it from outside, it would appear far wider than the Sun itself, a vast, invisible structure stretching millions of kilometers in every direction from Jupiter, and Europa orbits completely inside it every second of every day. It is worth pausing on just how massive Jupiter really is. When astronomers discovered the first planets orbiting other stars, the exoplanets, many of them were Jupiter-like objects, large, gas giant worlds orbiting close to their stars. Jupiter-like planets appear to be common in the universe. They form readily from the disk of gas and dust around young stars. Their large masses allow them to gather hydrogen and helium, the most abundant elements, before those gases dissipate. And where Jupiter-like planets form, they may carry icy moons, moons with oceans, moons like Europa. The question of whether Europa-like moons are common elsewhere in the galaxy is not answerable today. We cannot yet detect moons around other stars. Our telescopes are not sensitive enough, but the existence of Jupiter in our solar system, with its family of large moons, including at least one probable ocean world, possibly more, suggests that the phenomenon may not be unique. If giant planets are common, and if they naturally acquire icy moons, and if tidal heating in those moons is sufficient to maintain liquid water, then ocean worlds may be numerous, distributed across the galaxy, orbiting their gas giants, cold and bright from the outside, possibly liquid on the inside, waiting, as Europa has been waiting. The magnetosphere is not an empty space, threaded with invisible field lines. It is an active environment, an energetic one. Charged particles, electrons and ions, are continuously fed into Jupiter's magnetosphere from multiple sources, from the solar wind, the continuous stream of charged particles flowing outward from the Sun, from Io, the innermost large moon of Jupiter, and the most volcanically active body in the solar system. Io's volcanoes continuously eject sulfur and oxygen ions into the space around Jupiter. These ions are captured by Jupiter's magnetic field and accelerated. The particles trapped in Jupiter's magnetosphere do not simply drift gently along field lines. They are accelerated to very high energies. Some electrons are moving at a substantial fraction of the speed of light. They accumulate in bands, regions of concentrated high-energy radiation, called radiation belts, analogous to Earth's Van Allen belts, but far more intense. Europa orbits squarely inside these belts. Every second of every day, the radiation that strikes Europa's surface comes from this environment. It is not occasional. It is not seasonal. It is continuous. A relentless rain of high-energy particles from a source that never turns off. For any spacecraft in Europa's vicinity, this radiation is a serious engineering concern. Semiconductor materials, the transistors and memory cells that form the basis of modern electronics, are damaged by radiation. High-energy particles pass through them and change the arrangement of atoms, alter the electrical properties of materials, create defects in crystal structures over a sufficiently long exposure. These changes accumulate, instruments behave unexpectedly, data becomes corrupted, systems fail. The Galileo spacecraft, which studied Europa and the other Galilean moons from 1995 to 2003, experienced radiation-related anomalies. Throughout its mission, its tape recorder, the primary means of storing data before transmission to Earth, experienced failures. Its memory was corrupted on multiple occasions. The mission team worked around these issues with remarkable ingenuity, but the radiation was a constant constraint. Europa Clipper was designed with all of this in mind. Radiation-hardened electronics, shielded components, a spacecraft designed to survive nearly 50 close passes near one of the most radiation-intense environments in the solar system. But shielding has mass, and mass is always a constraint. The design represents a careful balance, enough protection to survive the mission, not so much that the spacecraft becomes too heavy to launch. The effect of radiation on spacecraft electronics is measured in a unit called a rad, a radiation-absorbed dose. Different components tolerate different doses before they begin to malfunction. Some can handle millions of rads. Others fail at much lower levels. At Europa's orbital distance from Jupiter, a spacecraft receives radiation at a rate that would deliver a very high cumulative dose over the course of months. This is why the mission was designed with nearly 50 brief flybys rather than a continuous orbit. Each flyby contributes a carefully calculated increment to the total radiation dose received by the spacecraft between flybys. When the spacecraft is at the far end of its wide orbit around Jupiter, the radiation rate is much lower. The electronics have time to recover slightly, or at least to not accumulate additional damage quickly. The mission is designed around a total radiation budget, a maximum lifetime dose that the spacecraft can receive and still function. The number and timing of flybees is planned to stay within that budget while maximizing the science return. It is an unusual constraint for a spacecraft mission. Most spacecraft are not operating inside the radiation belts of a gas giant, but Europa Clipper was built for this. Its designers knew where it was going, and they built a machine that could survive the environment long enough to tell us what it found. Here is the tension that defines Europa as a scientific subject: the same moon, the same world, two completely different realities, depending on where you look. At the surface, cold, irradiated, airless, hostile, a place where the radiation environment is severe enough to damage electronics over relatively short exposures, a place where the temperature would freeze any liquid instantly, a place where there is no atmosphere to speak of, just the faintest wisp of oxygen produced by radiation chemistry on the ice, too thin to breathe, too thin to provide any protection, a place where, from the surface looking up, Jupiter fills much of the sky, enormous, banded, relentless, its heat presence the source of the radiation, the source of the tidal forces, the source of the gravity that shapes everything here. Now look beneath the surface, below the ice, possibly only a few kilometers down in some regions, perhaps tens of kilometers in others. The radiation does not reach. High-energy particles lose their energy as they pass through matter. They slow, they are absorbed, they deposit their energy in the material and stop. The ice absorbs the radiation. The ocean below exists in a radiation environment that is far gentler than the surface above. Not zero radiation, but far lower, low enough that the chemistry of the ocean is not being torn apart continuously, the way the surface chemistry is, low enough that the water, and whatever it contains, can exist without being constantly broken down and rearranged by energetic particles from above. The ice does something remarkable. It is not just a physical barrier, it is also a radiation shield, a kilometers thick layer of material absorbing the radiation and protecting what lies beneath it. And so the moon that looks so hostile from the outside, surrounded by lethal radiation, frozen, airless, cold, may carry, just a few to tens of kilometers below, that forbidding surface, one of the more protected environments in the outer solar system, warm possibly, chemically active possibly, shielded from the worst of the radiation by the same ice that makes the surface so unwelcoming. The same world, two entirely different faces, the danger above and the possibility below are not contradictions. They are part of the same planetary system, the same set of forces that make the surface hostile also keep the interior warm, keep the ocean liquid, keep the chemistry cycling. Europa is not dangerous despite what it might contain. It is the way it is: radiation, ice, ocean, heat, because all of those things are expressions of the same underlying reality, a moon in the grip of a giant planet, shaped by that grip in every way, carrying the consequences of that proximity from its outer surface down to its rocky core. The contrast between the surface and the interior of Europa is not unique to this moon. On Earth, we live on the surface. The surface is where we built everything, where life evolved, where the oceans and atmosphere interact, where sunlight drives energy. But deep below the surface of Earth, miles down in rock and pressure, there is also life, bacteria living in rock pores, organisms sustained by chemical reactions between rock minerals and groundwater, communities that receive no energy from the sun and have no connection to the surface world. The deep biosphere of Earth, the living world beneath the surface, may contain a significant fraction of all the microbial life on our planet. We are accustomed to thinking of the surface as life's home, but life does not see it that way. Life goes wherever the conditions allow it, wherever there is water and energy and chemistry, even in rock, even underground, even in places so deep and dark that the very concept of sunlight is irrelevant. Europa forces us to extend that thinking beyond Earth, to consider that the relevant environment for any chemistry, any potential life, might not be the surface of a world, but its interior, not what the world looks like from space, but what it is like, kilometers inside, where the ice meets the water and the water meets the rock. The surface is just the outside. The inside is what matters. Europa Clipper is a large spacecraft by the standards of interplanetary science missions. It is one of the more substantial instruments humanity has ever sent into the outer solar system when its solar arrays are fully deployed. The two large wings that capture sunlight and convert it to electricity, they span more than 30 meters from tip to tip. To put that in perspective, 30 meters is roughly the length of a city transit bus, measured 5 times end to end. That span is not for appearance. It is a requirement imposed by physics. At the distance of Jupiter from the sun, sunlight is faint. The intensity of sunlight follows an inverse square law. It decreases with the square of the distance from the sun. At Earth's distance, sunlight delivers about 360 watts of power for every square meter facing the sun. At Jupiter's distance, more than 5 times farther away, that number drops to roughly 50 watts per square meter, less than 4% of the sunlight intensity that reaches Earth to generate enough electrical power to run all of its instruments, and particularly to operate everything simultaneously. During the intense but brief window of each flyby, Europa Clipper needs to capture sunlight across a very large area. The enormous solar arrays are that area. The spacecraft also carries batteries that store energy between periods of solar charging and can provide additional power during peak demand, but the solar arrays are the primary source. Large, delicate, carefully deployed wings of photovoltaic cells facing a sun that is little more than a very bright star from Jupiter's perspective, delivering its faint energy to a spacecraft that has traveled hundreds of millions of kilometers to receive it. Europa Clipper launched in October 2024 from Kennedy Space Center in Florida, on the east coast of the United States, on a rocket powerful enough to lift this large and carefully shielded spacecraft out of Earth's gravity well and into interplanetary space. And then it was on its way, not directly to Jupiter, in interplanetary navigation. Feet, the straightest path between 2 points, is rarely the most efficient. The planets are moving. The spacecraft is moving. Fuel is a finite and precious resource. The geometry of the solar system offers opportunities, ways to use the gravity of planets you pass near, to change your speed and direction without spending fuel. Europa Clipper used this strategy. The design of Europa Clipper reflects decades of lessons learned from sending spacecraft into difficult environments. The Galileo mission to Jupiter, which operated from 1995 to 2003, was not designed primarily for Europa. It was a mission to the Jupiter system as a whole. It studied the planet, the magnetosphere, and all four Galilean moons. The Europa data it returned was extraordinary, including the magnetic evidence for the ocean, but Galileo's instruments were not optimized for the specific measurements that Europa's ocean most requires. Europa Clipper is different. It is designed for one purpose: to understand Europa, specifically Europa, not the broader Jovian system. Though it will learn things about that too, its instruments were chosen specifically for the measurements that the ocean questions demand. Its orbit was designed specifically to maximize Europa science while managing radiation exposure. Its shielding was calculated specifically for the radiation environment. At Europa's orbital distance, every major design decision was made with Europa in mind. This is the advantage of a focused mission. When you know exactly what you are trying to learn, you can build exactly the tool to learn it. And Europa Clipper is that tool, the most precisely designed instrument humanity has ever aimed at this particular question. The technique is called a gravity assist. When a spacecraft approaches a planet closely, the planet's gravitational field pulls the spacecraft in keet, bends its trajectory a keet, and releases it on a different heading. If the geometry is right, spacecraft departs faster than it arrived. The planet loses a tiny, essentially unmeasurable amount of its orbital momentum. The spacecraft gains a significant boost. The energy is conserved overall. The planet gives, the spacecraft receives. The exchange is real, physical, governed by Newton's laws. It is not magic, just the careful exploitation of the solar system's natural geometry. Europa Clipper performed a gravity assist at Mars early in its journey. Then, several months later, another gravity assist at Earth, swinging past its home planet, Kaut, borrowing momentum and departing on the trajectory that will carry it to Jupiter. After that Earth flyby, Europa Clipper was committed outward, past the orbit of Mars, past the asteroid belt, that broad, diffuse region of rocky bodies, orbiting between Mars and Jupiter, into the cooler, darker, more distant reaches of the outer solar system, toward Jupiter, toward the radiation field, toward the ice. The journey takes roughly 6 years. Europa Clipper is expected to arrive at Jupiter in 2030, 6 years. During that time, the team on Earth continues its work. Instruments are calibrated by testing them on known sources. Software is refined. The detailed plans for each flyby are developed, reviewed, and revised. Scientists study every new measurement of Europa, made by other instruments, by the Hubble Space Telescope, tight by ground-based observatories, incorporating the latest knowledge into the mission's planning. The spacecraft moves, the team prepares, the years pass, And at the end of the 6 years, Europa Clipper will be at Jupiter, and its real work will begin. The time Europa Clipper spends traveling between Earth and Jupiter is not wasted. It is an opportunity for calibration and preparation. Before a spacecraft arrives at its target, scientists use every available resource to refine their understanding of what they will find. New observations of Europa from Earth-based telescopes, new analysis of old Galileo data using more sophisticated methods, new laboratory experiments that test what happens to ice under conditions similar to Europa's, new theoretical models refined by better computing power. All of this feeds into the mission planning, the detailed plans for each flyby, which instruments to prioritize, at what altitude to pass, which region of the surface to target, are continuously updated. As the scientific team's understanding improves, by the time Europa Clipper arrives at Jupiter in 2030, now the team will have spent those 6 years preparing for every flyby in extraordinary detail. The first flyby of Europa by a spacecraft in the 21st century, a spacecraft designed specifically for this moon, will not be improvised. It will be the result of decades of planning, of everything learned from Galileo, of thousands of hours of instrument calibration, of trajectory optimization, of scientific debate about which questions to ask first, the years of travel, the years of preparation. The spacecraft moves, the science team thinks, and both arrive at Jupiter, ready to do what they came for. When Europa Clipper arrives at Jupiter in 2030, the work begins in earnest, but not immediately at Europa. The spacecraft will first be captured into orbit around Jupiter itself, not around Europa. This is a deliberate design choice, driven by the same radiation concern that shapes so much of the mission. An orbit directly around Europa would provide constant proximity to the Moon. Every part of the surface would be accessible. Every measurement could be repeated over time. It would be the ideal configuration for thorough, systematic study. But an orbit around Europa would also place the spacecraft continuously inside the most intense region of Jupiter's radiation belts. The cumulative radiation dose would be far higher than Europa. Clipper was designed to withstand. Electronics would degrade faster. The mission would end earlier. The science would be compromised. By orbiting Jupiter instead, the spacecraft spends most of each orbit at a greater distance from Jupiter, where the radiation is significantly weaker. It swings inward to Europa's vicinity only during the flybys, then retreats back out along its wide Jovian orbit. The total radiation dose over the planned mission is carefully managed. Each flyby contributes a specific increment to the cumulative dose. The mission is designed so that the total exposure across all planned flybys remains within what the spacecraft can tolerate and still function. The flyby trajectories are calculated years in advance. Each one is designed to pass over a specific region of Europa's surface at a specific altitude, at a specific angle. Some flybys are designed for low altitude, passing within just a few tens of kilometers of the surface for maximum sensitivity in gravity, chemistry, and radar measurements. Others are designed for slightly higher altitude, to achieve broader spatial coverage of surface chemistry and magnetic field. Nearly 50 flybys are planned, spread over several years, of orbiting Jupiter, each one a different piece, each one adding to the picture, a slow, systematic, patient reading of a moon that has been keeping its interior from any external inspection for 1 billion years. The nearly 50 flybys of Europa are not all created equal. Some will pass over the poles of the moon, some will pass over the equator, some will skim just above the surface. Others will observe from a greater height. The combination of different trajectories allows the mission to build a complete picture. A single flyby over a given region at a given altitude gives one slice of information. A second flyby over the same region at a different altitude adds another perspective. A third flyby from a different angle adds a third. Each flyby reveals something the others cannot. Each fills in a part of the picture that was missing. By the end of the mission, after all the planned flybys, after all the data has been transmitted and analyzed, scientists will have a data set unlike anything that has ever existed for Europa. Not a complete picture, not a full solution to all the mysteries. Science rarely delivers that, but a much clearer picture, a picture with specific features identified, specific measurements made, specific hypotheses confirmed or ruled out. And from that picture, the next questions will emerge. What do we now understand that points toward the next mission? What have we learned that tells us where to drill, or where to send a lander, or which specific feature to target with a more capable probe? Europa Clipper is not the end of Europa exploration. It is the beginning of the serious phase, the phase where guesswork gives way to measurement. One of the most fundamental things Europa Clipper will try to determine is the structure of the ice shell. How thick is it in different regions? Is there significant variation from place to place? Are there regions where the ice is thinner, where the ocean is closer to the surface? Are there places where liquid water exists not just below the ice, but within it, subsurface lakes or pockets embedded in the ice shell itself? These questions matter enormously. A very thick, relatively uniform ice shell, 30 or more kilometers everywhere, would suggest an ocean that is deeply isolated from the surface. Exchange between the surface chemistry above and the ocean below would be slow, constrained, limited. The oxidants created at the surface by radiation would take an extremely long time to reach the ocean. The chaos terrain and the lineae would be the product of processes operating deep within the ice, with little direct connection to the ocean beneath. A thinner ice shell, or a shell that varies significantly, would suggest a more dynamic Europa, places where the ocean is closer, places where exchange is faster, places where the surface geology most directly reflects what the ocean is doing below. The radar instrument on Europa Clipper will probe downward through the ice. On every flyby, radio waves penetrate ice well, but they reflect at boundaries, at interfaces between materials with different properties. Ice and liquid water have dramatically different electromagnetic properties. Solid ice and warmer, more fluid ice have somewhat different properties. ice and rock are very different. By analyzing the reflections, their timing after the transmitted pulse, cult, their strength, cult, their character, scientists will determine the depth of these boundaries. Beneath each point on the surface, over many flybys is tight, covering different regions of the moon. These measurements will accumulate into a three-dimensional map of the ice shell's interior, a map